Hey everyone! Welcome back to our series on security testing techniques and validation frameworks. Today, we're diving into two essential methods for identifying vulnerabilities in systems: static analysis and dynamic analysis. Whether you're a cybersecurity enthusiast or working in the field, these methods are crucial for building more secure, resilient systems. Here's a quick look at what we'll cover today: the basics of static analysis, what it is, why it's important, and the types of tools typically used. Then, we'll explore dynamic analysis, understanding how it works during system execution, the tools involved, and the unique insights it offers. Let's start with static analysis. This technique involves examining code and system components without actually executing them. Imagine assessing a car's blueprint before it's built. With static analysis, developers can spot design flaws early in the development phase, even before a single line of code is run. In static analysis, we're looking for structural issues or logic flaws that could open the system to security risks. It's like a fine-toothed comb for your code. The key benefits of static analysis include identifying coding errors, such as hard-coded passwords or weak encryption, that could become vulnerabilities if left unchecked. Some common tools in static analysis include code review tools and automated analyzers. For example, code review tools, either manual or automated, scan the code for issues, much like an engineer reviewing every component of a car's design for potential weaknesses. Automated analyzers, meanwhile, act as intelligent assistants that quickly flag code sections with potential errors or security flaws. One of the best aspects of static analysis is that it promotes early detection. By identifying vulnerabilities before the code is executed, developers can address issues in the design or logic, which saves time and resources in the long run. This early detection is incredibly cost-effective because the complexity and expense of fixing issues increase once the code has been deployed. It's like catching an error in the blueprint stage of a car design. Correcting it now costs a fraction of what it would take to fix it after the car is built. Now, let's move on to dynamic analysis, which is all about observing the system during actual execution. If static analysis is like reviewing the blueprint, dynamic analysis is the test drive, putting the system through its paces to see how it performs under real conditions. This approach is particularly powerful because it allows us to monitor real-time interactions within the system and detect vulnerabilities that might not be obvious in a static review. During dynamic analysis, we use tools like debuggers and monitoring tools. Debuggers help test and troubleshoot the system as it runs, allowing developers to inspect variables, step through code, and pinpoint errors as they arise. In automotive systems, for instance, a debugger could reveal unexpected issues in the vehicle's control software when responding to different environmental inputs, like changes in sensor data. Then we have monitoring tools, which track the system's performance and behavior in real time. This is essential because dynamic analysis focuses on real-time insights. By observing how the system responds to various inputs, monitoring tools can reveal if a system slows down, crashes, or exhibits unusual behavior when handling unexpected inputs or attacks. In an automotive setting, monitoring tools might reveal a memory leak in the software controlling the car's navigation or infotainment system, an issue that could potentially cause the system to fail mid-drive. Identifying runtime vulnerabilities is the core strength of dynamic analysis. Certain vulnerabilities only show up when the code is executed, so static analysis may miss them. For example, a timing vulnerability could cause a delay or crash when the vehicle's control system receives simultaneous inputs from multiple sensors. By running the system and tracking its response to different scenarios, dynamic analysis provides a deeper understanding of its resilience under real-world conditions. So, to recap, we looked at two important types of security analysis. Static analysis focuses on detecting vulnerabilities early by examining code without executing it, which is more efficient for finding structural issues. Dynamic analysis observes the system in action, which helps catch vulnerabilities that appear only during runtime. Both methods are essential for a well-rounded security strategy. We often recommend a combination of static and dynamic analysis to cover both early-stage and runtime vulnerabilities, making the system far more robust. Thank you so much for joining us in this video. Be sure to check out our previous videos in the series. including our recent deep dive into fuzz testing and how it stresses systems with malformed data to find weaknesses. Also, don't forget to like this video, subscribe to our channel, and leave a comment below if you have any questions or topics you'd like us to cover next. Your support helps us grow and bring more valuable content your way.